Here's a problem where you'll have to pull off a clever math trick in order to answer a question the way they posed it. An object of mass m on a string is whirled with increasing speed in a horizontal circle as shown above. When the string breaks, the object has speed v0, and the circular path has radius r with a height h above the ground. Neglect air friction. Determine the tension T, the tension in the string, which is at a slight slant because of the angle they showed us in the diagram, just before the spring breaks. In other words, when the velocity was equal to the v0 that they gave. Express your answer in terms of capital M, R, v0, and g. I would like to start this problem like I usually do, by picking an axis to work with and drawing a free body diagram. In the x-axis, according to my diagram here, I ought to have one force pulling me to the right. The component of the tension in the string that acts along the x-axis, we will call it T cosine of theta. That's because it is adjacent to the angle here. Now, if I look at a Newton's second law summation, I could say that the sum of the forces in the x-axis is equal to T cos theta. And then by Newton's second law, I can say that the sum of forces is equal to ma. But hold on a second, what kind of acceleration am I talking about? I'm of course talking about centripetal acceleration. So really it would be proper for me to say mac is equal to T cosine theta. But what really is the definition of centripetal acceleration? It's v squared over r. R being the radius of the circle I'm working in, which is given to me as r, and v being the velocity described at this moment of time, just before the string breaks, which was v0. So mv0 squared is equal to T cosine theta. At this point, it kind of seems like this was pretty easy. I just need to solve for the tension, right? But wait a minute. You know the mass, you know the velocity, you know the radius, and you're looking for the tension, but you don't know this. So I could divide both sides by cosine of theta, but I wouldn't be answering the question the way they posed it. They explicitly said to express my answer in terms of m, r, v0, and g only. And that's something you really have to look out for on the AP Physics exam in particular. We do not have enough information to keep working with this equation, although it is complete and correct. So we're going to have to go to the other axis to see if we can get more information. If I consider what's going on the y-axis, as usual, I have the force of gravity, mg, pulling me down. But if this ball is not currently falling, but rather in the horizontal circle, there must be something pulling it up. And we will call that the y component of the tension in the string, T sine theta, because of its association with the opposite side of that triangle. Now, if I sum up all the forces in that axis, some of the forces in the y-axis, the first thing I would find is that it was equal to 0, because it's not accelerating up or down. Actually, I'll go ahead and do that in the next step. But I'll set it equal to T sine theta for pulling us up minus mg for pulling us down. So 0 equals T sine theta minus mg. And because of the equilibrium, we may say, adding mg to both sides, that mg is equal to T sine theta. This is all the information I can get from the other axis, and it's all the information I can get from the problem. Unfortunately, it doesn't tell me exactly what to substitute for cosine theta. It tells me what to substitute for sine theta. But sometimes it's useful to remember some trigonometric identities. Let's recall the identity sine squared theta plus cosine squared theta equals 1. And let's try and get this information into a format where I can use this fact. First, we're going to square both sides of both equations. That's going to give me m squared v naught to the fourth over r squared equals t squared cosine squared theta. Over here on the right equation, m squared g squared is equal to t squared sine squared theta. Now watch what happens if I add the two equations together. I can always add the left with the left and the right with the right. Let's use purple to represent the fact that we're going to combine these two equations and see what we get. Slightly weird looking m squared v naught to the fourth over r squared plus m squared g squared is equal to t squared cosine squared theta plus t squared sine squared theta. And we're getting closer. Because now if I take that right side and I factor out the t squared, note that also in this step I'm going to factor out the common factor of m squared on the left just for the sake of neatness. See m squared v naught to the fourth power over r squared plus g squared. Okay, here's the important part. We're factoring out t squared now, and we're getting cosine squared theta plus sine squared theta. Of course, that is exactly what I want to see, because I intend to say that this is equal to 1 by this identity here. And so the tension is almost done. We have here t squared equals all this stuff on the left. Let's take the square root of both sides. We'll take the square root of m squared, which is m, and then the square root of a much more complicated expression, which I won't bother rewriting in another way. I'll just put the radical sign over it. V squared to the fourth power over r squared plus g squared. The whole group will be equal to the tension. And that completes this part of the problem. The problem then goes on to ask a slightly more elementary question, based in kinematics rather than dynamics. Determine the time required for the object to hit the ground after the string breaks. I've drawn a side-on view of this diagram and what we would expect to see. Here we see that the string will break right here, and that it will carry on a slightly parabolic path in two axes, 2 dimensions, as it falls down and to the right, and we're interested in the time it takes to reach the ground. Now, because acceleration is taking place in the y direction, and because displacement that we're interested in from here to here, from here to the ground, is taking place in the y-axis, we should consider the things that go on only in the y-axis, and that's going to help us decide which kinematic equation to use. Now, the way we decide which kinematic equation to use is basically coming down to which one works. And I want to draw your attention to the third one. Delta S, displacement, equals initial velocity times time plus 1/2 a t squared. Do we know enough information to use this equation? I argue that yes, we do. We know the displacement of the trip that we're interested in if we remember to keep our thinking in the y-axis only. The displacement goes from here to here. It's falling down in what we'll call the negative direction. We say that the displacement will have a magnitude, a value of negative h. That negative sign is going to be important in a few seconds. We say that the initial velocity, remember, in the y direction. Who knows what the velocity in the y direction here is initially? It's equal to 0. It has nothing to do with this whatsoever because that's taking place instantaneously in a different axis. We are able to zero out this entire term. Finally, we have positive 1/2, but then the acceleration. What do we use for acceleration in a situation like this? Again, restricting ourselves to the y-axis. We are, of course, in Earth's gravitational field, where acceleration, according to my sign convention, we will say, is equal to negative g. So in place of acceleration, we place negative g. And so we have enough information. We know g, we know h, they are values that have been given to us, or they're constants, and we just need to find the time. And notice how, because we have been consistent and we have two negative signs, they cancel out. Really, h is equal to, 1/2 g t squared. To get t by itself, we're going to have to multiply over the 2 and divide by g. So we'll have 2h over g is equal to t squared. Taking the square root of both sides and writing from left to right, t will be equal to radical 2h over g.